Hello everyone, this is Huck. Welcome to ICIP 2021. Today I'm going to introduce our work, Robust, Unsupervised, Multi-Object Tracking in Noisy Environments. So this is Huck from Georgia Tech with my co-author Mohi from Hitachi, Ichie Liu from Georgia Tech, Kong Chen from Hitachi, Yoshinaga-san from Hitachi, Murakami-san from Hitachi. So first, I will talk about the task about multi-object tracking and unsupervised learning. So when we talk about tracking, we actually want to tag one or more objects over a sequence of frames. For example, if we have a video and we want to do the object detection in each frame. But when we talk about multi-object tracking, is in the video, we have all objects and want to tag its motion over the sequence. So this multi-object tracking is really empirical and have a wide application in the real world. So another thing is they can also depend on the category. For example, vehicles, pedestrian, traffic signs. Although this kind of image are various, but eventually we want our algorithm can track those kind of objects in input video. So why this task is challenging and may be a good way to combine with unsupervised learning. So when we talk about unsupervised learning, mostly we request know to read these labels. But multi-object tracking actually is one of the tasks highly rely on labels. For example, if you look at this image, saying we have a football player like Messi around a lot of Brazilian football player, but if each frame we want to generate this bounding box, they will be really expensive. So they will have a challenge if you want to apply multi-object tracking in industry, because usually we don't have those data set for different kind of application. So collecting this data and labeling this data take a lot of money and time. So how could we reduce this cost? Can we train a model without this kind of bounding box if we have an input video? For example, if we have an input video without this bounding box, and we train a model can generate this bounding box on a really few label validation set. This will reduce a lot of costs. At least for training data, we don't actually need this label in an unsupervised sense. So this motivate a recent 2 or 3 years development on unsupervised multi-object tracking. So mostly it can be categorized in two major methods. The first one is use probability modeling. For example, we have a vibrational autoencoder with a discriminator to have the image-to-image regression doing this video. And then as a byproduct, in some state, we can generate this bounding box, and then we use this bounding box for evaluation. And we have the regression loss, but for the validation, the byproduct, we can also evaluate on the multi-object sense. Another way is based on the geometry modeling. For example, if we use some geometry rendering a fruit frame from a certain object, like this kind of training can be also possible without the bounding box. So in this work, we are discuss one of the SOTA results in the probability modeling and one in the geometry modeling in recent work. But when we talk about generalization and robustness, what it could be a challenge in multi-object tracking. For example, when the multi-object tracking highly rely on these like multi-label data, if the tracker algorithm without this label, one hypothesis could be if the tracker highly rely on the intensity to do this prediction. For example, for mixed video, we can see there is a huge intensity difference from the input image and the background. Although that the algorithm look at this unsupervised tracking, but right now they don't really have in-depth discussion about how this noise will affect this algorithm. So this is our first motivation. How does noise impact unsupervised MOT? And could we improve both generalization and robustness in multi-object tracking? What we mean generalization is if the model is not just learning this intensity, but also the shape, can a certain algorithm transfer well from one dataset to another similar dataset? For example, it's possible to transform from this Arabic number to some kind of character if there are similar domains. So here is our contribution in this work. So first, we investigate the robustness challenge in multi-object tracking in unsupervised way. For example, for the clean input sequence, there is shoes and clothes that are drifting, but in a noisy unsupervised multi-object tracking, there's a noise in behind. So if your algorithm overfit on the intensity, they will have some like degradation. And furthermore, we propose a new self-attention unit architecture to improve and trying to resolve this issue. And finally, we propose two unsupervised MOT video dataset, so which is inspired by mixed video, but combined with more complex image. For example, fashion image and kuzushiji image, which is the Japanese character. So we divide the problem in two case studies. The first one, in regarding our robustness, so we are looking at additive noise study. So we are simulate channel noise, for example, in digital sensor like CMOS, overheat, and trying to simulate this additive Gaussian noise on the input image. And then if the model still attain a higher accuracy, which indicate a better performance independent from background noise. For example, we can have a mixed and there is a noise in behind. And furthermore, talking about a generalization challenge. So if we scramble the input image, but the model still rely on the intensity to make the prediction, so we can also look at the robustness in terms of the content we actually learn. So we remain the same pixel-wise intensity level on the object, but we scramble the image, something like this. But here is actually the image scrambled from mixed. You can see originally should be some numbers, but after this scrambling, they look really different. But if the model still have a high accuracy, which means this unsupervised MOT may overfit on the intensity. So here is our proposed self-attention unit geometry modeling methods. But one thing we really argue is because this, when we look at the object detection, the visual pattern inside a certain content, which means the bounding box is also important. So we also leverage upon the UNet, which have a skill-free representation learning. So for each time, if there's an input frame, so they will go over self-attention unit to have the skill-free learning and have the self-attention on the visual pattern. And then the tracker array will generate a certain prediction for each object. And they will also have a sequential learning from the previous array by the LSTM, which is motivated by previous work by He, tracking by innovation in CVPR 2019. And then this multi-object location will be generated, but the frame is not generated. So finally, they will have a compositional rendering based on geometry, and then we calculate the loss from this geometry rendering output and the original input frame, such as autoencoder loss. So in this sense, by training this model, we don't actually need this bounding box label. But from the evaluation, we can have the byproduct in the triangle array and the locations. So before we look at the result, let me introduce some new data set we introduced. So the first proposed data set is Hiragana Kuzushiji multi-object tracking data set. So there's some ki, su, na, those kind of Japanese hiragana is from the ancient book. So there is a effort from the researcher to provide a Kuzushiji means. So we use this means data set and extend it for video version. So right now you can see there is some character drifting around in the video, and potentially they can work for different domain like textbook or those kind of video. And second, we also know the fashion means is a much complex version of means. So we also make a fashion means video to evaluate our algorithm. So ideally, a well-trained means they will have a better generalization on the Kuzushiji means instead of the fashion means. And to have a baseline and reproducible study, so we also compare some previous video data set like the means MLT video and Atari MLT video, which is trying to tracking the numbers and trying to tracking the Atari and these bullets in a Atari gaming video like Space Invader. And we also have two new data sets to see can we have more complex development. And also as a byproduct, we also have a scrambled means MLT video, which is try to have a noisy task to see if the model is really overfit on the intensity. So first let's look at the MLT accuracy versus noise ratio in means and Atari. So the x-axis is a noise ratio. For higher noise ratio, which means they have higher chance to receive this Gaussian noise. For there's a higher SNR to receive this Gaussian noise. And for the MLT accuracy, which means the accuracy in the MLT matrix. So we can find out when the noise ratio increase, actually the most of the model, the performance decrease. But if we actually add this UNet to have the skillful learning doing the geometry rendering, the model actually improve a lot from the baseline geometry-based modeling methods in MLT. And also in the Atari dataset, we can have the same phenomenon. So both of UNet-based, like attention and ResNet-based UNet, like multi-object tracking encoder actually learn a better performance. Same thing happened in the Kuzushiji means, you can see actually the performance improve. And also for the fashion means, they have the performance improve even then there's a higher noise ratio. So MLT model shows a degrade performance when the noise ratio increase, which is our first observation. And the second is proposed ResNet, UNet encoder and attention UNet encoder degrade least compared with tracking by innovation and the CLOT, which is the probability-based encoding methods. Finally, if we look at scramble means and UMLT results, we can find out the performance of pre-trained UMLT on the means MLT when we test on the scramble means objects. Those methods can still learn well, which means they might rely on the intensity information to make the prediction, which is not making sense. And second, if we look at different UMLT model for the adaptation, we can see the RES UNet and attention UNet, they have a better generalization in terms of transfer learning result, which means they may really learn the real patterns. So finally, we have some conclusion. Our study highlighted challenge in archiving robustness and generalization on supervised MLT, and proposed method attained a good result. And the proposed data set and scrambling task will be helpful for further research. And for future work, we can look at a universal noisy training, low complexity modeling, and also conditional MLT. Thank you.